Hello guys, check out this demo. What appears to be little tiny beads are blocking the words physics fun. As water is poured over them, for some reason the words become more and more visible. What exactly is going on here? So today, we're going to be working on index of refraction, Snell's law, and dispersion. All things that help us determine how we see objects. So first off, how do we see transparent objects? In the case of these Orbeez, we can see them when they're surrounded by air because the index of refraction for the air and the Orbeez are different than each other significantly. This bends the light around the beads so that we can't see the words physics fun. But as water fills this container, the water and the Orbeez have the same index of refraction, or close enough, that the light doesn't get distorted as it travels through that medium. Let's take a closer look at these Orbeez. When they're submerged in water, they're very hard to see because they have almost the same index of refraction as the water surrounding them. On the other hand, we can clearly see the water-air boundary, and we can clearly see the plastic-air boundary because those index of refraction are significantly different than each other. Just a quick reminder, index of refraction, N, is a unitless figure in physics. It's the ratio of the speed of light in a vacuum to the speed of light in the material. One thing that these demos show is if two objects have a close enough index of refraction, it's hard to distinguish their edges, and therefore they remain transparent. So for instance, if we take this fundamental photograph showing a glass rod in water versus a glass rod in oil, we know that the oil and the glass must have the same index of refraction because we can't see its boundary in oil, but we can in water. And double checking against the index of refraction, oil and glass, crown glass that is, have approximately the same index, and therefore it's very difficult to see that this tube extends all the way to the same depth as the one to the side of it. But how did scientists measure these indices of refraction anyways? It's relatively difficult to measure the velocity of light in a medium. If I wanted to use the distance and time equation, I would need miles and miles and miles of that medium in order to measure a reasonable time. If I wanted to use the wavelength equation, I would need to make standing waves, which isn't always feasible when I'm talking about waves like X-rays or radio waves. Instead, what we can use is Snell's law. Snell's law says that if I have a boundary between two different materials, like air and water, that the product of their index and the sine of their angle should be constant. That means if I know the index of one material, let's say the air is my incident material, I would take my index of refraction from air, measure the angle, and use it to find the index of refraction in water. In this way, we can measure angles and use those angles to calculate index of refraction. In your homework set, you will use Snell's law equation in order to find missing index of refraction on the PhET simulation. But for now, let's give you an example of how this equation works.
Okay, so for the problem we're going to try today as a sample, let's say we have red light leaving this fish, and it goes from an index of refraction of 1.33 into an index of refraction of 1. As this red light leaves the fish, it hits this air-water boundary at an angle of, let's call this, that looks like about 30 degrees. Nice easy number to work with. So this is my incident angle, is 30 degrees. And let's see if we can figure out the refracted angle using Snell's law. So Snell's law relates the two indices of refraction, so that's Ni sine theta sub I is equal to Nr sine theta sub R. We have our two indices. The initial index is 1.3, and that initial angle in water was 30 degrees. That goes into air, so that refracted index is 1, sine theta. So, let's solve. Dividing by 1 on both sides, well, that gives me a 1. That's easy. 1.33 sine 30. For this, do make sure your calculator is in degrees. This gets us the left side of the equation is 0.665 equals sine theta. And how do we get rid of a sine? Well, we're going to use an inverse sine. So we're going to take a sine inverse on both sides of the equation. Sine inverse on both sides of the equation. And that gives us an angle of 41 degrees. Equals theta. So let's draw this correctly. That means as it goes from water into air, that red light bends away from the normal line, making an angle larger than 30 degrees. So the light was going to go here, but it's going to bend away from the normal, making a larger angle. And so a person who's trying to catch this fish, right? Let's say this is our person, they've got like a spear, this is like Tom Hanks in Castaway. They're going to go try and catch this fish. They actually don't see the fish where it truly is. Our brain thinks light has traveled in a straight line, so actually thinks that the fish is shallower than it truly is. That creates all sorts of optical illusions when refraction occurs. But at the end of a problem, always double check for sense making. This is going from a slow material, so that should be the slim angle. The slimmer angle is 30 degrees. To a fast material, because there's fewer particles in the way for air than there are in water, the fast material should have the fatter angle. That's 41 degrees. And that's how to use Snell's Law.
And so, my friends, for today, you're going to be practicing using Snell's Law equation by going into the PhET bending light simulation. You'll use the protractor tool from the left-hand side to measure the angle of incidence, in this case 60 degrees, compared to the angle of refraction, in this case maybe 37 or so degrees. Since you're measuring from a simulation, there will be some reasonable estimation here. As needed, you can change the wavelength of light. You can also, if you'd want to check your work, measure the speed of light in the material and use that to calculate index of refraction in a separate way. You'll also be taking a look at light as it goes through prisms, and especially white light, which instead of being monochromatic, meaning one color, white light has all the colors of the rainbow. Best of luck to you, and as always, email with questions.